The next question is kind of mathematical, and it's perhaps aimed more at data scientists or places that are looking more for someone who knows algorithms a bit, but I think anyone can get it. And the question is, how can we calculate the mean square error between two lists of numbers? Now here's the thing. So let's say I have a list of numbers here. So let's say I have, first list equals 10, 20, 30. And the second list equals 12, 18, and 35. What we want to know is how close is the second list to the first list? Now this might seem like a kind of funny thing to do, but if you imagine that these are the predictions and these are the actual results, then it makes sense. For example, consider that the first one would be a weather forecast, and we want to know how close was our weather forecast to the actual result. So what we're going to do is compare it somehow. Now, how can you compare it? There are a variety of different ways to do it. Now, I should add that if you are doing any sort of numeric analysis, you are probably going to be using NumPy for it. But one of the stipulations that I was given in this question when someone passed it to me, suggested it to me, was you're not allowed to use NumPy to make this calculation. You must do it in pure Python. Now, from an efficiency standpoint, that does not make sense. NumPy is so much faster than working with numbers in pure Python. But from a thinking perspective, from a using Python perspective, this is actually an interesting problem. So how would I find this out? How would I calculate it? Well, one way is I could just sort of do the difference, element by element. The thing is, you can't really do that because the difference might be positive, might be negative. And so if you take the mean of that, if you take the average of that, you're probably going to get into trouble because the sort of positive and negatives are going to cancel each other out. That's why it's very common to use the mean square error. Meaning what we're going to do, meaning we are going to take the difference between every two items at the same index. And what we're going to do is take that difference and then square it. And square it, of course, means that it's going to be positive by definition. And then we'll take the mean of that, and then we can figure out what that is. So how am I going to do that? Well, one way, and if you're coming sort of from a C kind of background, it might make sense to then, create a new list with the difference from each element. And what we can do is maybe iterate over the indexes from 0 to whatever the max index is. So here's what I'm going to do. I'm going to say here the errors, or we can even say the square errors, equals an empty list. And then what I can do is say for I in range, and we'll say len predictions. And we're going to assume here that predictions and actual results have the same number of elements. If they don't have the same number of elements, bad news for everyone. And what I can do is I can say square errors equals, and we'll say here prediction. Well, we'll say predictions I minus actual results I. Well, actually, we're not. Yeah, I. And then we're going to do that times 2, or not times 2, to the second power. And then we're going to say, not square errors equals square errors append. Ha ha ha. Already getting it wrong today, and it's not even that far in the morning for me. All right, and I need an extra set of parentheses here. And when I'm done with this, you're going to see that we now have the square difference, right? So the first one is off by 2, so we get 4. Second one's also off by 2. By -2, we're going to get 4. Third one's off by 5, so we're going to get 25. How am I going to calculate the mean then? Well, I'm just going to do the sum of square errors divide by the len of square errors, and that will indeed give me what I'm looking for. And so this works. This is actually what we would want. But is it the way we would want to do it? Almost certainly not. And the reason is, well, there are at least 2 reasons here I can think of. One is that in Python we typically don't use the indexes. The indexes are there only when we want to number something, when we want to see something, but iterating over the indexes of a list or anything else is pretty unusual, and I would say un-Pythonic in many ways. The second thing is, why am I creating this new list square errors in this way? I'm creating an empty list, and I'm adding to it one element at a time. A much more Pythonic way to do it would be to use a list comprehension. And list comprehension is almost always going to be the right answer when you have one sequence and you want to turn it into a second sequence. You want to sort of map it from one to the other using an expression to describe the difference between one and the other. Okay, so if we're going to do a list comprehension here, are we going to do it over predictions? Are we going to do it over actual results? What if we do both? What if I could take predictions and actual results and line up each of these pairs so that 10 and 12 were together, 20 and 18 were together, 30 and 35 were together? That would give me then the pairs that I need to perform these operations. And the way I'm going to do that is with the zip function. Zip is a built-in function. If I say zip on predictions and actual results, well, it gives me a zip object. That's not really helpful for our purposes, but if I put a list around it, we'll see. It's basically a list of tuples. Nowadays in Python 3, it's an iterable, but it's a list of tuples. And now I have these two things and those two things and those two things. So what I can do is I can say a list comprehension sort of like this. I can say here, one prediction, and let's do this. I'm going to say one prediction, comma, one result, for one prediction and one result, in zip of predictions and actual results. A little wordy there, I'll admit. And I now am getting the actual list that we got from zip. Okay, this is not super exciting, but how is this working? Well, zip is creating a new iterable based on predictions and actual results, where index 0 from predictions actual results is the tuple at the zip's 0. Index 1 from predictions actual results is the result of, is at zip 1, and so on and so forth. So now I have these. Now what I can do is I can say actually, one prediction minus one result to the second power. And now I have that. So I've basically created the same list as we had before, but with less code, and it's actually more efficient to do it this way. Now, of course, at the end of the day, I'm going to have to put this into a variable. So we'll say here, square errors equals that. I'll make a little adjustment here, not because we have to, but just think it makes it a little more readable. Okay, and now I can take a look at square errors. It's going to be the same thing. And how can I get the mean squared error? I can say the sum of square errors divided by the len of square errors. Now, again, is this what NumPy would give me? Yes, NumPy would make it easier, faster, more efficient. But to understand this exercise shows that you have to understand how to work with parallel data structures. And when you're working with them, almost certainly you're going to want to use the zip function at some point. And then combining zip with a list comprehension really makes it easier to do this sort of thing. All right, on to the next question.